Hi, my name is Chris Nunn, and I'm the product manager for our high-speed serial devices. I'm very excited to talk to you guys today about MGT Debug for the NI PXIe-6591R and 6592R. Before we dive into the MGT Debug examples, let's have a quick overview of the hardware. Our fastest high-speed serial module is the NI PXIe-6591R. This is rated for line rates up to 12.5 gigabits per second per channel and has 8 RX and TX channels on a single device. This is all enabled through the Kintex 7 K410T FPGA. We've also have 2 gigabytes of DRAM that's connected to this FPGA, and we've implemented a PCI Express Gen 2x8 connection to a host PC or embedded controller running Windows. And this allows sustained data rates of 3.2 gigabytes per second between the FPGA and host. This is very important for stream-to-disk applications, or anything that needs a lot of data in the Windows environment. The connector type chosen for the SerDes signals was Mini-SAS HD. This was done for the high density that allows 4 TX and RX pairs in a single connector. We have both passive copper cabling options and optical cabling options for the SerDes lanes, and we also have 20 single-ended DIO through a VHDCI connector that's routed directly to the FPGA. This is very useful for low-speed DUT control such as SPI or I2C. The 6592R is rated up to 10.3125 gigabits per second and has 4 TX-RX pairs. It shares the Kintex 7 410T FPGA, the same DRAM, and same host streaming bandwidth, but the connector type here is SFP+. We chose SFP+ for the SerDes connectors because it's common in the industry, especially in networking applications. For our cabling options on the 92R, we have both passive copper and optical, and we also have 4 single-ended DIO lanes that are tied directly to the FPGA through SMB connectors. So now let's jump into the MGT Debug content. To do that, I want to show the system I have on my desk. Particularly, we're interested in the PXIe-6591R, which is the card here that has the 2 cables connected to it. This is a single cable connected in loopback mode, and the diagram on the right shows what that looks like. When port 0 is connected to port 1 through Mini-SAS HD connectors, I mentioned that there was 4 TX and RX pairs per connector. That means that TX0 and RX0 get connected to TX4 and RX4. 1 goes to 5, 2 goes to 6, and 3 goes to 7. This will be important as we do demonstrations throughout the rest of this video. When you open the zip file, this is what you will first see. There's an MGT Debug Getting Started PDF file that's really great because it's documented and it walks you through the installation process, an architecture overview with system diagrams. It has a section on customizing with the GTX toolkit. So these are all VIs that allow you to make your own example. We've got about 7 examples that this document explains, but there's no reason you can't customize. And all of this actually does not require LabVIEW FPGA knowledge. These are all host VIs that can configure the high-speed serial cards to do different things. So once we open this up, the first example I want to start with is an equalization example. So the first thing I'm going to do is choose the PXIe-6591R and choose a line rate. You'll notice we have a lot of options here that are common to specific protocols. For this example, I'm going to go with our fastest 12.5 gigabits per second. We then get to choose different patterns that we want to generate for our test. These pseudo-random bit sequences are commonly chosen to mimic different protocols with different encoding schemes. For this example, I'll just choose one, the PRBS23 pattern. Now we have our transmitter settings. If I'm going to transmit on lane 0 and I want to look at what that transmission looks like, I should set receive to lane 4. That's based off the diagram we just previously looked at. When I run this, we will now start generating a PRBS23 pattern at full rate on lane 0. We ran an eye scan to get a capture of what that eye looks like. So the way iScan works is it calculates bit error ratios at different locations of the eye and plots all those results on an intensity graph. This allows us to view the link margin, where the wider the eye, the better the physical connection of the SerDes TX and RX pairs. If I change the differential swing on the transmitter to its lowest setting, let's say 270 millivolts, peak to peak, and do another scan, we will notice that the eye has significantly shrunk. There is also an ability for us to change the equalization mode on the receiver. If we go to DFE mode and do another scan, you'll notice that the eye looks different. So what this shows is the DFE equalization is actually better at recovering the 270 millivolt peak-to-peak transmitter setting, and that's because LPM is the low power mode where DFE is the more complicated 5-tap equalization circuit. If we go back to LPM and crank up the voltage a little more, we can do another scan, see that it's bigger, and then there's also abilities to add pre and post emphasis. Just to show you that this is doing something, I'm going to add a lot of both and run another scan. You'll notice that this can completely close the eye, and in here you'd have a lot of bit errors and not have successful communication. This is one example of different transmitter and receiver settings that you can change and how you can view and debug and determine the best settings to have a successful link communication. The next example I want to show is in our basic connection and debugging folder, and it's the basic PRBS pattern and generator checker. Once again here, I'm going to choose the 6591R. We can choose any rate we want. Maybe this time we do 10.3125 gigabits per second. Now when I run this, it's going to start generating on all lanes this 10.3125 gigabit per second pattern. And we have individual settings here to change the PRBS sequence. Right now these are all in near-end internal loopback, so that means it's looping back inside the multi-gigabit transceiver and not actually even through the cable. If we change to a normal connection, I can then decide to receive on channel 4, and we have no errors now. That's because we're using the cable. And what this is showing is at a 270 millivolt peak-to-peak swing, we've got a 0 error count, and it's calculating a bit error ratio around 2 times 10 to the minus 12. That number will continue to get smaller as we let samples build up. I can force errors on purpose, and we can see the error count increase as I do that. I can reset the error counter and calculate a new bit error ratio. I can even add pre and post emphasis. What you might start to see is, if you remember from the last example, if we crank those up high enough, we'll start to see bit errors. Right now the eye is so closed from this pre and post emphasis that our error counter is maxed out. I'm going to reduce that some and reset the error counter. So this gives you low-level access into forcing errors at PRBS patterns. You can also change. So as soon as I change the pattern, we're seeing errors until I match it on both the TX and RX side. But this allows you to generate and check different patterns, change your transmitter settings, and your loopback modes, all at whatever line rate you chose on as many lanes as you want. The last thing I want to show off is this multi-lane iScan report. So once again, I'll choose the PXIe-6591R. I'm going to say that I want to generate a report. Let's just pick, I don't know, 6.25 gigabits per second. I'm going to bump this up so it runs a tiny bit faster. This is just the resolution into our offsets here, and I'll click run. What this is going to do is generate this PRBS7 pattern at 6.25 gigabits per second, and we're going to run iScan on all 8 lanes in parallel. The nice thing about this is because I've said generate report, it generates a nice HTML report where it gives me information about the device, the bit file I'm using, and then actually plots the eyes of all these different lanes. You'll notice our lane 4 is still closed off. That's because I was modifying those settings in the previous VI, and I had high values of pre and post emphasis. But this is a nice report that gives you a view of what all the different lanes look like. So that's a quick overview of MGT Debug. Make sure to check out all the examples and read more in the Getting Started PDF. Thanks for listening.